Hello everyone, and thanks for watching Edupedia World videos. This is the second lecture of calculus where we will see the geometric meaning of differentiation and we'll study integration. So the geometric meaning of differentiation is the slope of the line which is the tangent to any point on the function. Let me make that clear. So let's say we take our original function which we took last time, y is equal to x cube, but we plot it in a little bit more detail now. And let's say we take two values x0 and x1. So this is the point x comma y at x0, and this is the point at x1. If we say that x1 is x0 plus delta x, then the length of this line is delta x. Similarly, let's call this y0, which is x0 cube, and let's call this y1, which is simply x1 cube. So this will be delta y, which is y at x1 minus y at x1. And let's say we complete this triangle. What is delta y by delta x? We know it's the derivative of y with respect to x. That's what we saw last time. But it also has a meaning in this particular graph, which is if this angle is theta, then delta y by delta x is tan theta. Right, perpendicular by base. So we see that delta y by delta x, not only is it the change of y with respect to x between 2 points, it is also the tan of the angle which the line joining the 2 points makes with the x-axis. This, by the way, the tan of the angle which any line makes with the x-axis is called the slope of that line. It's a purely mathematical concept. So a line like this, which is parallel to the x-axis, makes an angle of 0 degrees, so it has a slope of 0. Slope is represented by m, which in this case would be tan theta, and theta is 0. A line like this, which makes an angle of 45 degrees, it would have a slope of 1, which would be tan of 45. A line parallel to the y-axis would have a slope of infinite, because it would be tan of 90, and lines like this would have negative slope. So the slope of a line is nothing but the tan of the angle which that line makes with the x-axis. Right. Now let's take the second part of the question. Earlier in the last lecture we saw this is how we calculate the derivative of y with respect to x, or rather the change in y with respect to x between 2 points, where the derivative is defined as the change at a particular point. So let's say we move x1 closer to x0. So the line which had made an angle of theta earlier, the angle was slightly decreased. It would be this line. Even closer it would be this line. Is getting harder to see now. But if we took the value at x, then what would that be? By just approximating it closer and closer, we can see that in that case the value would be the slope of the tangent at x. Right? You take two values near each other, the line joining them is called the secant. But if you take one value, it will be the tangent. So this is also another meaning of the derivative of y with respect to x. The derivative of y with respect to x on the graph is the slope of a tangent line with respect to x. If you draw the graph of y versus x, at any point you take the tangent, you calculate the slope of that line, that will give you the derivative of y with respect to x. Now again, if we take the derivative of a function not with respect to x but with respect to something else, for example, let's say the function y is sine of x cube, and we plot it versus x. I don't know how the graph is going to be. Let's say it's going to be something like that. At any point now, the tangent will give me the slope of this curve, and since this curve is between sine of x cube and x, the tangent will be the derivative of sine of x cube with respect to x. But if I do the same thing in a graph, which is of the sine of x cube with respect to x cube. That is, now x is not plotted on the x-axis, x cube is plotted. And if it comes out to be something like this, then at any point the slope of the tangent will be equal to d of sine of x cube by x cube. And you need to look at the terminology. This is y versus x. If you draw the graph of y versus x, the slope of the tangent will give you derivative of y with respect to x. Y and x could be any functions, no matter how simple or complicated. So this is the geometrical meaning of the derivative of y. Now there is a concept related to this geometrical meaning which is very useful in trying to calculate the maximum or minimum values of the function. So let's say I have plotted a function and it has two sections, one of them near which it has a minimum value, the other near of which it has a maximum value, and we need to calculate this point. So let's say this is my function. I'm only interested in the graphical properties now, so I'm going to draw it. So this is my function. This point, and let's say there are other functions like this. So this point and this point and this point and this point, all these points have a particular property, which is that the slope of the tangent is 0. At all these points the tangent is parallel to the x-axis. That means it has a slope of 0. Right? Such points are called critical points. The definition of critical points of a function is basically any point at which the slope is 0. So let's say I was given the function y is equal to x cube minus 4x. How do you find the critical points? You just calculate the derivative. dy by dx would be 3x square minus 4. So the critical points would be x is equal to plus minus 2 by root 3. Critical points are all those points where the derivative of the function is 0. Right? Now, this particular, let's assume that the function ends between these 2 points. This particular value of the function is the maximum possible value which the function ever takes. And this is called the global maxima. Similarly, this point is called the global minima. Global, as the name suggests, tells us that this is the global minima, which is the minimum possible value of the function over its entire range. But all 4 of these points, these 2 in particular and these 2 in particular, have other separate names, which are local maximas and minimas. So a local maxima is simply a point which is the maximum value of the function in its immediate neighborhood. So in this immediate neighborhood, we see that this point has the maximum value. In this neighborhood, we see that this point has the maximum value. So both these points are local maximas. However, this point is the global maxima. Similarly, both these points are local minimas. However, this point is a global minima. So we know how to calculate now local maximas and global maximas and local minimas and global minimas. They will be the points where the derivative of the function is 0. So let's say we calculate the derivative and it turns out to be 0. How do we know whether it's a maxima or minima? So there's a further test developed to be able to calculate that. Let's consider this point. This has a derivative of 0. So at this point f dash of x is 0. Similarly, at this point f dash of x is 0. So this is a point of similarity between the two, that they both have a derivative 0. Let's look at the immediate neighborhood. Before this becomes 0, f dash x is positive. We can tell that it's positive because the line is sloping in the first quadrant, so the angle which it makes with the x-axis will be between 0 and 90 degrees, so its slope is positive. On the other hand, this line immediately after the maxima has a negative slope. Similarly, this line has a negative slope, and this line has a positive slope. So we see that near a maxima, and this will always be true for a maxima, before the maxima the slope is positive, then it's 0, and then it's negative. So during a maxima, f dash of x is decreasing, but during a minima, f dash of x is increasing. So we found a point of difference between the maximas and the minimas. Near the maximas, f dash x is continuously decreasing, while near the minimas, f dash x is continuously increasing. But we can put that into a more familiar language using calculus. If a function is increasing, then its derivative is positive, and if a function is decreasing, then its derivative is negative. So if f dash x is decreasing, that means the derivative of f dash of x is less than 0. Keep in mind, this is the derivative of the derivative. So let's say the function is x cube. The derivative would be 3x square. The derivative of the derivative would be 6x. Right? So this is the second derivative of the function. This is also referred to as d2f by dx2. This is just a notation, and what it is really is called the second derivative. Similarly, near a minima, the second derivative is positive because f dash x is increasing. So d of f dash of x by dx is greater than 0. Right? So this is the point of similarity, point of difference between the two. So at maximas, at all maximas of a function, df by dx is 0 and d2f by dx squared, which is nothing but d by dx of this function itself, of df by dx. This is less than 0. While at minimas, df by dx is 0. This is true for both. And d2f by dx squared, which is d by dx of df by dx again, that is greater than 0. So the first step, differentiate the function, equate it to 0, find all the critical points. Then double differentiate the function, and the points where the derivative is positive would be points of minimas, and the points where the double derivative is negative would be points of maximas. Right? So this completes differentiation. Now we'll look at basically what is the opposite of differentiation, which is called integration. So we learned now that the derivative of x cube is 3x squared. So the opposite integration simply means the integration of 3x squared is x cube. But again, there are many more subtleties. The derivative of x cube is 3x square, but only if it's taken with respect to x. Similarly, the integration of 3x squared with respect to x is x cube. But actually there is an even slightly more subtlety, because though the derivative of x cube is 3x square, the derivative of 5 plus x cube is also 3x squared, because the derivative of 5 is 0. 5 is a constant. So the integral of 3x squared with respect to x is not only x cube, it is written as x cube plus c, where c could be any positive number, any number at all. And the notation we use is d of x cube by dx is 3x square. This means this is the notation for integral. integral of 3x squared, and then we multiply it by what we're integrating it with respect, which is x. So it is x cubed plus c. This ultimately is the essence of integration. Now you might think that I'm slightly cheating you in that I'm teaching you integration as the opposite of differentiation, but it must be something else which comes down eventually to be the opposite of differentiation. That's not true. We don't even have a way to calculate the integration of any random function, like I showed you the ways to calculate differentiation, and most often integral is found by calculating the opposite of differentiation. So that is what it is. So we know that the derivative of tan x with respect to x is sec squared of x. What that immediately implies is the integral of sec squared of x with respect to x is tan x plus c. We always put c, never forget c, right? So the integral of sec squared x with respect to x is tan x plus c. What is the integral of sec x with respect to x? That's a pretty complicated function, and this is why you see why I always try to teach integration as simply the opposite of differentiation. Differentiation you can find out much easily, but it's much harder to find out the integral of sec x than it is to find out the integral of sec squared x, because you know a function whose derivative is sec squared x. That function is simply tan x. Right. Now, there are two separate types of integration. By the way, all this is the algebraic meaning of integration. In the geometric meaning of integration, it means the area of the function, which we'll see later. So in the algebraic meaning of integration, there are two separate types of integration. There is indefinite integration, and there is definite integration. In indefinite integration, we do have a constant of integration. Whereas in definite integration, we have no constant. So how does this work? Indefinite integration is what we saw right now. The integral of sec squared x dx plus c. In definite integration, we do not have a constant of integration directly, but we solve for it indirectly. For example, let's say we want to calculate the integral of a function 4x cube, right? So the indefinite integration would be x to the power 4 plus c, the integration of 4x cubed dx. Now let's say we were given two things. We were given that you need to find out the integration of 4x cubed, but we were also given that this particular function, let's call it y, we were given that y is equal to 1 when x is equal to 0. So we were given two things. We needed to find out the integral of 4x cubed, but we were given that the function which you need to find out, its value is 1 when x is equal to 0. So we know the function is x to the power 4 plus c. We'll put x is equal to 0 and y equal to 1. We'll get c is equal to 1. So this means y is equal to x to the power 4 plus 1. So when we integrate something indefinitely, we get a constant of integration, and sometimes we might be given some external conditions which enable us to determine this constant of integration. Now I'll show you a way to get x to the power 4 plus 1 without introducing this constant of integration at all. So in this case, we'll calculate the integral of 4x cubed dx, but what we'll do is we'll integrate it from, so we were given dy by dx is 4x cubed, so we need to find the integral of 4x cubed dx. Now if dy by dx is 4x cubed, then dy is 4x cubed dx. So the integral of 4x cubed dx is the same as the integral of dy. Now instead of calculating the integral of dy to be y and 4x cubed dx to be x to the power 4 plus c, what I can do it, I can put what are called the limits of the integration right here itself. So we know that y is 1 when x is 0, and let's say y is equal to y when x is equal to x. So what we do is we calculate the integral and we put the limits. So this is how we write it. Between the limits 0 to x, 4x cubed dx, x to the power 4, which is the integral of 4x cubed dx, is equal to y integral of 1 to y. And now we put in the limits and subtract. So x to the power 4 between 0 and x will be x to the power 4 minus 0, which is equal to y between 1 and y will be y minus 1. And from this we get y is equal to x to the power 4 plus 1. So we see there are two different ways in which we can integrate a function. We can either just calculate the indefinite integral, put in the constant of integration, and then try to solve for the constant of integration based on some other conditions which we were given. Or we can just put in the limits directly and never have to calculate the constant of integration at all. Right. Finally, there are, just like we had some rules for differentiation, we have some rules for integration which are basically the opposite of the rules for differentiation. So if we have a function x to the power n, the integral of that function is x to the power n plus 1. So this is the integral by n plus 1 plus c. And the reason this is the integral is because if I differentiate this, the derivative of x to the power n plus 1 will be n plus 1 times x to the power n. N plus 1 will cancel with this n plus 1. The derivative of c will be 0. So the derivative is again x to the power n. Right, so we see that integration and differentiation are just the opposite of each other. Now, this rule has a particular exception. This rule is valid except when n is equal to minus 1. And you could have seen that directly. If n is equal to minus 1, this becomes x to the power 0 by 0, which is not defined. So what happens when x is minus 1? That is 1 by x. We need the integral of 1 by x. Do we know any function whose derivative is 1 by x? Yes, we do. That's the function ln x. So that means the integral of 1 by x is ln x plus c. And the derivative of ln x plus c is 1 by x. The integral of sin x would be minus cos x. And the reason for that is the derivative of cos x is minus sin x. So the derivative of minus cos x would be sin x. There's a plus c here as well. There's always a plus c when you indefinitely integrate something. Similarly, the integral of sec squared x would be tan x plus c, which we differentiate and we'll get sec squared x again. So we see that integration and differentiation are basically the opposite of each other. Differentiation is the more basic one, it's the more concrete one. We'll be able to definitely find the differentiation of a function if it is ultimately made up of those 9 functions which we talked about. X to the power n, ln x, e to the power x, and the 6 trigonometric functions. However, you only know the integration of a specific number of functions, such functions which are the derivatives of known functions. For a random function such as sec x, it's very hard to calculate the integral. In fact, I'll tell you a fun fact. There is a particular function sin x by x, and it seems a simple enough function, but its integral is very complicated. In fact, you need to approximate it to try to calculate. So when you see a function you need to integrate, the best possible way to approach is try to think of a function upon which when you differentiate it, you would get this function. Right. This is the end of differentiation and integration. We'll be using it when we learn kinematics and motion in two dimensions. Thank you.